Welcome to the test one review session, Zoom session. Today I'm just going to be kind of walking through test one. There are people here. I don't know, there's probably 30, 40 people here. Thank you guys for showing up. I'll periodically ask you guys questions and let's keep it a good video product and respond to those questions as quickly as possible. Yeah, so I'll go question by question through here, kind of show my thought process, how I would answer this question, how I would be looking to get partial credit, how I'd approach each one of these things. And hopefully that can kind of give you a place to start in terms of kind of doing different practice problems, redoing this test again, going back and checking to see if you're thinking about the question the same way, or doing some lecture note questions to see how can I take this and apply it to a different question? Um, yeah, and I'll be here answering any questions anybody has. Yeah, so stick with me and we'll do this. So I'm going to put arrow pushing questions, and these aren't full mechanisms, i.e., they're not full like get from one product to the next product like you might have seen in Orgo 1. These are just one step mechanisms. These are either you're going to fill in the missing product based off the arrows, or you're going to fill in the missing arrows based off the products given. So this is just one transformation. This is one step of a mechanism. But what I'm really trying to see here is, do you understand what these arrows are communicating? Do you understand the flow of electrons that is implied by these arrows? So if I look at this arrow, I see this bromine sharing electrons with that hydrogen. So no matter what, if there's an arrow between two things, that product that is going to be in the final product. That bromine is going to be connected to the hydrogen. Since it was negatively charged and it's giving electrons away, it's now neutral. This hydrogen, the bond between the hydrogen and this carbon, right? This hydrogen has no electrons by itself, but it is connected to this bond made out of two hydrogens. That broke off, and those two electrons went here. So if I look at this other product, what's happened is I like drawing in a question like this, I like drawing the starting material. The hydrogen was taken away and those electrons ended up here. Now, since this carbon was positively charged in the beginning, it got electrons. It is no longer positively charged. It ends up neutral. Okay. So this is a step based off of um, the electrophilic aromatic substitutions we talked about the other day. So this one's a little bit more complicated. There's a few more things going on here. So just like always, I like drawing my starting materials out, and then we can kind of move them. So I see that this bromine, based off this bottom arrow here, this bromine has to be connected to this carbon. So I'm going to redraw that kind of in a more flattering way. This bromine has to be connected to that carbon. Since this bromine is the one that gave away electrons, I'm thinking it's going to be positively charged, but we'll do the electron count later. This double bond went and attacked the bromine. So since this carbon already has two hydrogens on it, right? It had two hydrogens to begin with, so it still has two hydrogens. It can't make another bond. So that double bond has to be connecting this carbon to the bromine, right? That has to be what that's communicating, right? Because a bond happens between two atoms. It uses those electrons to form a bond with that carbon, that bromine. Then this bond breaks and goes to the bromine, which shows up as a lone pair instead of a bond. So this bromine gained electrons. It's negatively charged. If I count this, this bromine lost a pair of electrons, it gained a pair of electrons, and then it lost another pair of electrons. So that's a net loss. So when I lose electrons, I get a positive charge. So I want you to think step by step. If you're lost on something, redraw the starting materials, do it one arrow at a time. Okay? Now this is what I want you to do when you see this. You see sodium hydroxide, I want you to draw the ionic form. It's going to make everything a little bit clearer. So every time you see a metal, the thing it's attached to is negatively charged. So just go ahead and draw it out. I'm going to get a smaller pen. So what I see has happened is there's a bond that occurs between that oxygen, between this carbon and this oxygen, right? This bond is formed. This oxygen becomes neutral. So in order to have this happen, electrons from this oxygen have to go to that carbon. These two electrons are forming this bond. So this is a pretty straightforward addition into a carbonyl or into a carbocation, right? It's giving its electrons. Notice the sodium's, I didn't even write it. It's just there. It's implied. You don't have to write this. It's just there. We don't care about it. There's no carbon on it. It doesn't do anything else in the equation. Oh. I'm missing something here. All right. Let me give you what we're missing for these two questions. Yeah, that's my bad. Sorry if you got there and it was confusing. So, in order to figure out what's happening, we have to take a closer look at what changes, right? What changes from the starting material to the final product. A lot of people's first temptation is to say, well, this double bond moved here, right? We it looks like that double bond moves there. That's really tempting to say. And honestly, if I gave you this question on a test, I'd expect pretty much 90% of the wrong answers to look something like this. But that's not really what's changed. The double bond is just electrons. It's not substantial. There's something much bigger that's changed from the starting material to the final product. Somehow, this final product has gotten a negative charge, right? That means we've probably removed some sort of proton, or we've somehow made this negatively charged. So I started looking. This carbon has no protons. How many protons are on this carbon?
Two.
There's two, right? If I look at the same carbon in the final picture, how many protons are on it now?
One.
There's one. So it's very tempting to say the bond moved, but something way bigger moved. A proton was removed. An implied proton was removed. That's kind of the trickiest bit about this one is that proton's removed whether or not I draw it out or not, right? Like whether or not I drew it in the first step and drew it again in the second step, it's still been removed. There's still two protons in the starting material, one in the final product on that carbon. So I know that this oxygen has to gain electrons. It goes from neutral to negative. Most likely, that oxygen is gaining electrons from this double bond. That's the most available place it could have possibly gotten electrons from. This oxygen is the only thing that could possibly take one of those hydrogens, which is something that we need to have happen. We need to take that hydrogen because there's one less hydrogen in the final product. And the things that take hydrogens are usually like have to have electrons. Then we just want to take the hydrogen, we're going to leave this bond behind. So that's how I'd answer this question.
I have a question.
Yeah.
Could you use like maybe like a bulky base or something along those lines to take the hydrogen instead?
Yeah,
Um,
what the base is it doesn't really matter.
like KOTBU is like fine for that.
Yeah, well, okay. So what I wouldn't expect you to draw something in. So this is I wouldn't do this on the test. That was my bad. I would
Oh,
include
okay.
some sort of base for you to use.
Okay.
Yeah, so I wouldn't expect you to draw something in. Every atom you need should be in there to start
Okay.
with. That was just my bad writing this practice test.
Thank you.
So this next one's the same question just backwards. So again, you might be thinking, well, this bond has to go up. But that doesn't really make much sense for a lot of reasons. One, this oxygen already has a full octet, so it can't take more electrons. Two, the oxygen has a negative charge, so I doubt electrons are going to want to flow towards a negative charge. That seems unlikely. More likely is that the negatively charged oxygen is going to want to give electrons, and there's a newly formed bond here that it could give those electrons to. That would explain the double bond there. But the problem is that this carbon already has four bonds. And then we notice something. We notice the exact opposite. There's one hydrogen here and two hydrogens here. So we need to justify adding a hydrogen to this carbon. So we can kind of get two birds with one stone here. This double bond, we can just use to get that proton and leave behind those electrons, satisfy that positive charge. So that justifies every single thing we can see in our picture. The charge is flowing away. The electrons are flowing away from a negative charge. We're forming every bond we need to form. We're justifying going from one proton to two protons on that carbon. So I think these are tricky because it has to do with implied hydrogens. Those hydrogens are there whether or not they're drawn. We just save time not drawing them all the time. Yeah, this is another one. We need some sort of base. It doesn't really matter. So yeah, we can use terp-butoxide. Again, on the test, I'll give you that base. That's my bad. So what's happening here? We have to take note of what changes from the starting material to the final product. Well, you might be tempted to say, well, we add a double bond here. Well, sure, that does happen. But how? Where do those electrons come from? If this were to do that, well, then I would get an addition product, which is not what I want. Somehow, I have to get electrons to this double bond. A big hint here is that um, I go from a positive charge to a neutral. Somehow I've lost a positive. So I start looking around. How many hydrogens are on this carbon?
Three.
There's three. And then there's two in the product. So again, this is the same kind of question. Somehow I need to remove a hydrogen, gain this double bond, and satisfy the positive charge. So I take the hydrogen and I leave those electrons behind. This is an elimination mechanism. Just like, I mean, this is very similar to an elimination mechanism. They're very similar ideas. When you have a positive charge, there's really two ways you're going to satisfy it. You're either going to add directly into the positive charge, which is what we see here, where we add the thing into the positive charge, we make the bond with the carbocation, or like we see here and here, we take the hydrogen adjacent to the positive charge, right? This is the elimination versus substitution thing. These are motifs that pop up all the time. Okay. So stop. I look at this question, I stop and I say, hold on, I've got a metal. Before I even do a single other thing, I'm going to draw this out. I'm going to draw the ionic. That, oops. That is the first thing I do every time. You see a metal, you see sodium, you see lithium, you see potassium, draw out the ionic bond. Don't even just draw it out. Another little thing that this question is kind of poking at is what is ET?
Ethanol.
ET is ethyl. So this is an oxygen, a negatively charged oxygen with an ethyl group on it, right? That's what ET means. So another part of this question is what is TS? What is this OTS?
Leaving group.
Yeah, this is a leaving group. So one of the things that this question is getting at is see this oxygen doesn't come from this. No, that oxygen comes from the OET. These groups are the same. So somehow I have to get the garnet oxygen onto this carbon, right? That's the new bond I've got to justify. So this is a leaving group. It's going to leave. It's going to be kicked off. And what does the kicking is that negatively charged oxygen. That negatively charged oxygen is the one adding to this carbon. But that carbon had 4 bonds already. So in order to make room for that oxygen, I have to kick something off. And that is what's so nice about leaving groups. I'm going to make this clear. All right, stop. I've got a metal. I'm going to draw out the ionic. First thing. Then I look at everything that's changed. Well, somehow this nitrogen lost a hydrogen. So that bond was broken. It's no longer positively charged. And I get H2 gas and sodium is sitting around. So if I were to guess, I'm going to be looking at this nitrogen has to be gaining electrons probably from that bond, right? I'm going to probably remove this hydrogen and leave those electrons behind. The thing that makes the most sense to take this hydrogen is this, right? This negatively charged hydrogen isn't stable, very good base. It takes this hydrogen. That justifies my 2 hydrogens being bound together to make H2 gas. It justifies my nitrogen gaining the electrons to no longer be positively charged. All right. What's the first thing I see here?
Metal.
There's a metal. This magnesium is a metal. And actually there's something kind of weird going on here. So I'm going to draw this out. I'm going to give a positive charge to that magnesium and a negative charge to that carbon. I'm going to draw that metal out. I'm going to draw that ionic bond out. And now you can see where these electrons right here, you can see where they're actually at, right? They're actually part of this carbon, right? That ionic form is more accurate. So if I think about how this mechanism actually looks, it looks like this. Oops. All right, it's that negatively charged carbon That's adding into this carbon. So I'm going to redraw my product. And now, attached to this carbon, this new bond I made, wait, let me redraw this. This garnet arrow is this garnet bond. Oops. So those two carbons added into this carbon. Then this second arrow, this arrow here, shows the bond between this carbon and oxygen, oops, breaking. And it also shows the oxygen gaining electrons. So you can leave it like this for the test. I would draw it looking like this, but they're equivalent answers. It's just redrawn slightly nicer. Feel free to stop me if you guys have any questions. All right, this one's a little bit more straightforward. I'm going to redraw my starting materials. All of this wedge and dash is just distraction. None of that's going on. So there's an arrow between two atoms. So there has to be a bond between this nitrogen and this carbon. So this garnet arrow, that represents this bond right here. Nothing else changed about the nitrogen. It's still bound to two methyls and a hydrogen. But since it was neutral and it gave electrons away, now it's got a positive charge. This double bond broke and went up to this oxygen, which was positively charged. But now the oxygen's still attached to the hydrogen. But now the oxygen's neutral because it gained electrons. It went from positive to neutral. Okay. So now we're on to the question about aromatic, not aromatic, or anti-aromatic. So there are three rules. Is it a ring? Is it fully conjugated? Does it have 4 plus 2 pi electrons? So this is a ring. Check. This is fully conjugated. There's double bonds all around the ring and or lone pairs and or charges. Both of these nitrogens are sp2, so I do not count these lone pairs. They do not get counted. And so I end up with 2, 4, 6 pi electrons. So this is aromatic. This is a ring, but there's an sp3 carbon here. So this is not fully conjugated. So this is not aromatic. This is a ring. This is fully conjugated. And there are 2, 4, 6 pi electrons. This is an sp2 like oxygen, so we do not count this lone pair. So we have 6 pi electrons. This is aromatic. This is just a benzene ring. We know this. It's got 6 pi electrons. This is aromatic. Even though there are other things coming off of it, I would still call this molecule aromatic. All right. This next one's a ring. It has two, four, or it is fully conjugated. There's double bonds and or charges and or lone pairs on every atom here. There's no sp3 carbons anywhere here, which is the killer of conjugation. So it's a ring, it's fully conjugated, but there's only 4 pi electrons. So if it follows every rule except it has four n pi electrons instead of 4n plus 2 pi electrons, that makes it anti-aromatic. The easiest thing I'll tell you is that fully conjugated essentially means there's no sp3 carbons. So having this sp3 carbon kills it. sp3 oxygen, nitrogen, fine, but an sp3 carbon specifically for both resonance, conjugation, it kills any sort of electron flow. So a carbon's only truly sp3 when it has no charges and it has no double bonds or triple bonds. It's just a regular carbon sitting there. So this is a ring. It is fully conjugated because I have double bonds and or charges and or lone pairs. I have no sp3 carbons in the ring. Um, and then it has 2, 4, and then these lone pairs count as part of the pi system. It's technically an sp2 carbon with lone pairs. This is an well, this is an sp2 nitrogen. It does not count, but the carbon lone pairs will always count. So this makes 6 pi electrons. That is aromatic. This last one, it's a ring. I have an sp3 carbon. This is not aromatic. Easy. Okay. So this part is the labeling of reactions. Are you keeping up with kind of how we're talking about reactions, how we're thinking about reactions? Do I have a nucleophile in this picture?
Yes.
Where?
The NH2.
Yeah, this is my nucleophile, the NH2, specifically the nitrogen. Do I have an electrophile in this picture?
Yes.
Yeah, it's the carbon attached to the carbonyl.
Yep, carbon attached to the carbonyl. Perfect. And then I have a strong acid. So acids give protons. Acids make things positive. If I want my nucleophile and my electrophile to share electrons between each other, I want to encourage this reaction to happen. What's going to happen is my electrophile, in the very first step, acid-base reactions are the fastest. They happen first and they happen discretely. They have their own step. So the very first step, acids give protons to electrophiles. So my electrophile is going to take a proton, and I'm going to draw that as a discrete step. That is its own step. It is done. Then, second step. Now, I've primed my electrophile. It's ready to go. It's ready to be attacked by the nucleophile. So I'm going to give the electrons from the nucleophilic atom to the electrophilic atom. Even though the oxygen has the lone pair, it cannot take extra electrons from the nucleophile. You have to attack the carbon every time. This pushes electrons up into the carbonyl, and you get this. This is why arrow pushing is so important, because when I draw these arrows, I need you to be able to understand what each one of these arrows is communicating, right? This first arrow from the nitrogen is explaining, so this garnet arrow is this bond. Those are the same electrons. It's the bond between that nitrogen and that carbon. This double bond goes up, and it actually turns into a lone pair up here, which neutralizes the oxygen. So this is what I'm looking for. Can you do these first two steps? Can you understand? I've got a nucleophile, I've got an electrophile, I've got an acid. That's what's going to happen. All right. Here's the same thing. This is my nucleophile. Specifically that oxygen. The lone pairs on that oxygen are going to be my nucleophile. This carbon, because OTF is a leaving group, this carbon is my electrophile. See. Uh-oh. I see a metal. I'm going to draw out the charge. Specifically, sodium hydride is a non-nucleophilic base. So while there are extra electrons on here, so this is a base, in theory, you could think this hydrogen is going to attack that carbon, but it won't. This is a non-nucleophilic base. It does not attack carbons, it takes protons. In order to catalyze the reaction we want to use the base to take a proton from the nucleophile. So where acids give protons to electrophiles, bases take protons from nucleophiles. So there's what I did there, I want to be clear about. There's actually a bond between this oxygen and hydrogen, and when I take the hydrogen, it leaves those bonds behind. But you can kind of show it like this as a shorthand, where you're kind of putting that arrow between the oxygen and hydrogen. All right, what does that leave me with? That leaves me with an oxygen with a negative charge, and I still have my electrophile sitting around. Make sure these are discrete steps. The base takes the proton first, and then I redraw my products. Then nucleophile, attack electrophile, kick off leaving group, and I should end up with this. So it's the same first two steps. Step one, nucleophile, or sorry, base, deprotonate, nucleophile, or acid, protonate, electrophile, depending on which one you have. And then step two, nucleophile, attack, electrophile. Those are the first two steps. I expect you to be able to do that. I expect you to be able to identify nucleophiles, identify electrophiles.
Because it says to only like show the first two steps, do we need to write
out on step 2, like what it would become, or showing the arrows enough to get full points on an exam?
You need to at least get here. That is
Thank you.
the second step. Like that is, it's not the full second step unless you show the product of the second step. Yeah, good question. All right. I've got a charge here. I saw potassium. I saw a metal. There's a charge. This is my base. This looks like a nucleophile to me. Right? It's an alcohol. This carbon looks like an electrophile to me. So we follow the same rules. Even though the nucleophile and electrophile are on the same molecule, we follow the same rules. Step 1, base deprotonates nucleophile. So base is going to take the proton from my nucleophile. Step 1. That leaves me with a negative nucleophile, right? We've now made the nucleophile a better nucleophile. This is like a picture perfect nucleophile. Step 2, nucleophile attack electrophile. Now, what makes this complicated? They're part of the same chain. So, I'm pretty sure I told you guys the shoe analogy, right? If I grab someone else's shoe, we make one long chain between us. But if I grab my own shoe, I make a ring, right? I form a circle. I fold in on myself. So when I see this, I think this ring is gonna, I have to make a bond between this atom, one, and the carbon. So they are two, three, four, five. So oxygen oxygen one has to be bound to carbon five. That means that I have a five-membered ring with the oxygen inside of it. What was on five was another oxygen. That oxygen was double bond. Oops. But now it's single bonded, right? We lost one of the bonds. The oxygen was neutral, but it gained electrons, so it became negatively charged. So this is just another twist in it. It can form a ring. You have to be careful. If it's part of the same chain, it will form a ring. All right. This is a new reaction, but it's not. So I've got my nucleophile. I've got my, well, this is my electrophilic carbon, right? This is an electrophile. And this, we learned the other day, this is an acid. It's a Lewis acid. So just like all these other ones, step 1, what happens?
Acid pronates electrophile.
Acid protonates electrophile. The thing is, we don't have a proton, but this acts as one big proton. It's an electron donor or an electron acceptor. So we're going to have the acid, the electrophile interact with the acid. Step 1. I'm going to redraw that better. The only thing you have to know about this one that's different is that the leaving group leaves first. So this forms, so there's an extra step here. So now I have a great electrophile because I have a very bad nucleophile. Benzene's a bad nucleophile. It can add straight into there, and we get this. Right? Nucleophile attacks electrophile, and we end up here. So that's what I expect you to be able to do. To see the similarity, right? I want you to notice that it's the same ideas. I still have a nucleophile, I still have an electrophile. This time my acid just looks a little bit different. All right, so someone said, oh, this was a while ago. Someone asked, where does the arrow come from in the first step? The electrons on the hydrogen? Question mark. I think they were probably talking about this. One of these sodium hydride questions, right? Yes, because, all right, so if I wrote sodium hydride out, right, there's a bond between them. There's two electrons being shared between sodium and hydrogen, but realistically, those two electrons, like you can draw it like this technically. That's not wrong, right? But instead of drawing these two electrons being shared perfectly between, which is implied in that line, we say, well, realistically, this hydrogen is closer to that, or this electron is closer to that hydrogen because of its electronegativity. So we're showing these electrons not as a covalent bond between the two, but as a lone pair on the hydrogen. I think that makes it a lot clearer that it is this hydrogen, the lone pairs there, that are attacking and taking a proton. But yes, this is actually it's not a proton anymore. A negatively charged hydrogen. That's what we call a hydride because it's a proton. It's a hydrogen with two electrons, where a proton is a hydrogen with no electrons. Okay, that's a good question. All right, so the next bit is just fill in the reactions. So I don't need you to necessarily label this. If you know the reaction, I don't necessarily need you to um, be able to do the full mechanism here. What I'm looking for, what I would suggest from you is to have an idea to be able to say well, I think this is going to be my nucleophile. I'm pretty sure about that. This is going to be that's a really good electrophile, right? It's got a carbonyl and a leaving group. In order for my benzene to be a nucleophile, I need a leaving group and I need this Lewis acid. So I have my nucleophile, I have my electrophile, I have a Lewis acid. I can do this reaction. This reaction works. So I know that eventually this is a very shorthand. This isn't really how the reaction works, right? We showed the full mechanism down here, but just an indication, we know that this benzene is going to add to this carbon and we're going to lose that leaving group in order to make room for the benzene, right? So then we're going to reform the benzene and we get this. Right? That's the kind of shorthand. If you just got this and you didn't label any other part of it, you'd get full credit. But I would suggest labeling it because if I make this question out of 5 and you label nucleophile, electrophile, Lewis acid, I can give you a point or two, even if your final answer is wildly wrong. right? It tells me that you're getting the bigger picture, right? When these reactions become obsolete, like when we're at the end of the semester and you forget about these reactions, we'll still be able to label things nucleophile, electrophile. All right, so someone asked me a really good question. This is what I was saying. This isn't the full mechanism. This just gives an idea. The full mechanism looks like this. Once the benzene adds into the electrophile, you do end up with a positive charge and a not full benzene, right? In order to make this happen, in order to do this nucleophilic attack, yes, this carbon's gonna lose out on electrons. The benzene, in this case, the next step would be some sort of base taking this proton and you regenerate this benzene ring. Right? You're always going to regenerate. Like if I gave this question, I asked for the product, that will be the product. But when you're talking about the mechanism, when you're talking about every step, talking about kind of looking at the reaction as a whole, this is an intermediate. It's not a long-lived intermediate, but it does happen. But you will always eventually regenerate the benzene ring. That will be the final product because it's just a stable place to be. Okay, so we haven't talked about the specifics of this yet. This is what's coming on Wednesday. Um, again, this is my nucleophile. This is my electrophile. I've got a leaving group. So, um, the thing is, what we're getting to, and what I'm going to talk about more tomorrow, is that because of this group, it dictates. Like if I think about this benzene could either add here, or I could have this double bond attack, or I could have this double bond attack, right? I could form all sorts of products here. Um, I'll just draw all the possible products. So depending on where you add this thing, right? We can either add it para to the nitro group. We can add it uh, meta, or we can add it ortho. Because of the nature of this, and again, we're going to talk about this more because this is what's called an electron withdrawing group. It's going to exclusively add meta. So for this question, that will be your answer. It's going to be the meta. You don't have to put the para and ortho. But the electronic nature of this group, um, determines where you add the next thing. Okay. All right. This is a question thrown in to keep you out of robot mode, to keep you out of just zombie mode. So I mean, this is a ring. It's not benzene though. Um, right? There's no double bonds here. So benzene can't be my nucleophile. Plus, I don't have a Lewis acid. right? So this is probably not a benzene reaction. What I see here actually is this is ethyl bromide. This is probably my electrophile. And this is probably my nucleophile. I see an alcohol, that might be my nucleophile. Sodium hydride, this is just a base. So probably what's going to happen is I'm going to deprotonate my nucleophile. My nucleophile is going to attack my electrophile, and I'm going to get this. I'm going to get a substitution reaction, right? Where eventually, that guy takes the proton, so he's gone, right? That the idea is the same here, right? And I don't have to draw out the full mechanism, but I have a good idea because I know the mechanism that somehow somehow this oxygen, my nucleophilic oxygen, has to be attached to my electrophilic carbon. And I'm going to get rid of the leaving group. So stay on your toes. Not everything's going to be a benzene reaction. All right, here's another one. Well, this looks like an electrophile. There's just all sorts of halogens on it. This is a Lewis acid, so that tells me that benzene is my nucleophile. Um, again, this is something that we'll talk about tomorrow, but I can add one of two places, right? Those two those two carbons, those two sets of carbons are equivalent to each other, right? So I can either add to one or I can add to two. They're the same. Um, so because this thing is so bulky, it can actually help us direct. It's going to be much harder to add into one than it will be to add into two. So when I add this bromine to two, it's going to look like this. All right, I'm going to preferentially add to the less bulky place when there's no other difference. And again, we'll talk about that on Wednesday. But right now, what I would expect you to know is that this Br2 with this Lewis acid is going to add a bromine to the benzene.
What tells us that the amine isn't part of the reaction at all? Just the fact that there's FeBr3 there?
Yeah, that's a context clue. Yeah, so you're saying like, why is this not just do that? That's not out of the range of realm of possibility, but yeah, it's more the context of what I'm trying to ask. Yeah, if I give you a Lewis acid, it's the bromine. If you do it the other way, like if you somehow like if you ended up like it in attached to a Br, which is kind of a weird looking product to begin with, but you can justify it with nucleophile attacked electrophile, you're going to get some partial credit there. But yeah, you see the Lewis acid, that tells me benzene's probably going to be my nucleophile. But yeah, that's a really good question. That's that's the kind of questioning that will get you far in this class going forward. Hey, I've got competing nucleophiles. When is one the nucleophile that's working and one that's not? That's a really, really good question. All right. I've got a Lewis acid, so I know benzene's my nucleophile. That means what do I need to pair it with to add something, right? I'm adding the CH3, right? So this is the new bond I'm creating. I mean, that's a methyl group. So if I've got a nucleophile and I want it to react with something. I want to add something to it. Well, first of all, I'll just balance this, right? That's the first thing I'll do. I have to add a methyl somewhere, somehow. Do I want that methyl to be nucleophilic or electrophilic?
Electrophilic.
Right. So what could I put on this methyl group that would allow it to be an electrophile? That something that might just, disappear. Might
A
just,
chlorine.
yeah, some sort of halogen, right? Chlorine, bromine, uh, commonly used as methyl iodide. It's a very potent electrophile. I actually use it to make meth. It's iodide's the best leaving group. So, but I would give full credit for this because right, you're thinking about this kind of happening, right? Where your benzene is replacing the chlorine, you're substituting out. But this is a product of thinking, hey, I've got a nucleophile, I need an electrophile. Okay. So I've got a benzene. This might be my nucleophile. It's tempting. Um, but then what is it paired with?
Chlorine.
What, there's a fluoride on it, right? But like what this? What is this? One, I don't see a Lewis acid anywhere. But then this, I mean, I've got a sodium. I'm gonna draw the ionic bond, right? No, that doesn't look like an electrophile to me. What does that look like?
A base.
Looks like a base. Looks like a nucleophile. Looks like something that wants to give electrons away, right? Um, so that makes me reevaluate. I mean, benzene's already not a good nucleophile, right? It doesn't want to be a nucleophile. We have to really convince it to be a nucleophile by giving it a Lewis acid. I mean, that looks like a nucleophile. So then I have to reevaluate. Do I have anything? Could this possibly be an electrophile?
There's a leaving group.
There is a leaving group on this. And we're actually going to talk about this on Wednesday. Again, this is hard to get. This is not a reaction that happens lightly, but I mean, yeah, I mean, this is possible. It's a nucleophilic aromatic substitution. So this happens, right? It says now the benzene is the electrophile, so we need to be careful. It can play both roles depending on what you pair it with, right? So this benzene actually is not don't think about it as a benzene. This is now an electrophile because I've paired it with the nucleophile, an a nucleophile. So I've got a Lewis acid. That tells me benzene's going to be probably my nucleophile. It's a pretty good hint. Um, this looks like this looks like a pretty good electrophile. There's a leaving group on it. So what do I do? Um, I think this nucleophile is going to add into that electrophile. But here's the problem. This is just a regular alkyl halide. After after it leaves because of the Lewis acid, I end up with this. That's ripe to have a hydride shift.
Do you always have to draw the hydride shift? Like if you just automatically do the rearrangement, will you get points off?
No, I just draw it out so you can see it. Unless I ask for the mechanism specifically, unless I say like explain why you get this product instead of this product.
Okay.
Like if it was just this question, if you gave me this answer, which looks like this, you would get full credit.
Okay, thank you.
I would suggest writing it out, if you have the time, because if you mess something up, it'll be better to give you partial credit. And even again, like let's say this answer box is out of 5 points. If you didn't do the hydride shift, you'd probably get 3 out of 5 points. If you still got the like, if you put this, you would still get some partial credit here. No, I added. But it's not right. It's not fully right. You have to be aware that there could be a hydride shift here. All right. And this is just BR2. Sorry, that's kind of a weird way to draw it, but essentially you're adding the bromine twice because there's not that incentive to reform the benzene, so I can add it twice. So I put a little summary here. I'm going to randomly interchange these kind of reactions. I'll throw in some SN2s, which is this guy. This is just an SN2. All right, just throwing some random substitutions to keep you on your toes. I want you to recognize benzene acting as a nucleophile. This is going to happen in the presence of Lewis acids like AlCl3, AlBr3, FeCl3, FeBr3. So you see one of those, benzene's going to be your nucleophile, period. I'm not trying to trick you there. Substituting out leaving groups with benzene, carbocation rearrangements when it's an alkyl. So alkyl is RX. So that's alkyl. So just a regular carbon group where that's what's called acyl. So acyl halides do not rearrange. Alkyl halides do. And then what we haven't talked about yet is the directing groups, substituent effects. So what's on the benzene ring dictating when you add the next thing or where you add the next thing. Yeah, the only time you'll see a rearrangement for these. Okay, so the family of reactions here when benzene's acting as a nucleophile is called a electrophilic aromatic substitution. This is the technical name. Because you are substituting the aromatic benzene with an electrophile. That's where that name comes from. So people call it EAS, electrophilic aromatic substitution. The only time you will get rearrangements is if it is an alkyl halide, if it is a leaving group not on a carbonyl. That is the only time you'll get a rearrangement. But almost certainly if I'm giving it to you, I'm probably looking for some kind of rearrangement. Whereas if this is an EAS, what would you guess this one is? The one on top. Notice the roles changed. In the one on top, the nucleophile is attacking the benzene, where the one on the bottom, the benzene is attacking somewhere else. So this is a nucleophilic aromatic substitution. Um, People actually usually write it SNAR, which is substitution of an aromatic ring, nucleophilic substitution of an aromatic ring. So instead of SN2, it's SNAR, doing a substitution onto a benzene ring. So those are the two families. You have electrophilic aromatic substitutions where benzene is acting as a nucleophile, but if you put a leaving group on benzene, it can act as an electrophile. But yes, the only time you'll get a rearrangement is through when you have an alkyl halide. Benzene acting as an electrophile. There's got to be a leaving group on benzene in order to do that. So that's what I was just talking about. And then I'll probably throw in a Br2 addition to benzene versus alkenes, just to keep you on your toes. Just so you know that like a Br2 addition here does add 2 bromines, but a Br2 addition here only adds 1. Because of the nature of the benzene, because of that last step of the mechanism. Because if you had bromine sitting here, it would not add into that carbocation. You would not get this. Because that is less stable than the one on top. Okay. Yeah, I'm not gonna throw in an elimination yet. We will get there. Um, we will review eliminations. But for now, the only time you'll see something that's an elimination directly is like an arrow pushing question. But yeah, I won't give you an elimination for these reaction questions yet. Um, like here, it's either gonna be a substitution, it's either gonna be an SN2, an SNAR, or an EAS. Um, right, but we will get to eliminations. Well, you need to indicate none of these create stereocenters. Um, so there's no stereochemistry here. Yeah, not a single one of these reactions made a stereocenter. So there is no possible stereochemistry we would be talking about. Actually that's not true. Well, this is a meso compound, but like yeah, if you had this, well yeah, now both of those are stereocenters. I don't yeah. That's review. I'm not gonna don't worry about that. Stereochemistry. If I want you to talk about like include stereochemistry, I'm gonna make it very clear that we're doing stereochemistry. All right. So this question, these spectroscopy questions, I'm gonna give you a bunch of graphs, and I'm gonna tell you that these graphs all correlate to one molecule. Make it. Mass spec, I wouldn't waste too much time. Um, there's a molecular ion at 118. You can't even see it. It's way over here. But using that, they've calculated this. So first thing I would do is degrees of unsaturation. So that's 2 times 5 plus 2 minus the number of hydrogens all over 2. That's 10, 12 minus 2 minus 10 is 2 over 2. That's a degree of unsaturation of 1. Since there's 3 oxygens, I'm thinking carbonyl. Probably. Good chance. All right, that's all I'm going to look at the mass spec. Carbon NMR, there's 1 sp2 and 4 sp3s. All right, don't waste your time. We'll we'll use this to double check later. But this does kind of give me the impression that I might be right, right? If it was a C double bond C, if my degree of unsaturation was a C double bond C, then I would see most likely 2 peaks in the sp2 region, but I don't. Also, the fact that there is one sp2 tells me that it's likely not a ring that's giving me my degree of unsaturation. All right. I immediately see an OH peak and a carbonyl. So, yep, verified that we've got a carbonyl. So that accounts for 2 of my 3 oxygens. So I'll tell you what, like at this point, every one of these pieces is some amount of points, right? So let's say this whole question's 10 points. You doing degrees of unsaturation, you sp3 versus sp2, OH for CO2. You know, you're looking at, you know, three or 4 points here, just full of partial credit. But then where we want to spend all of our time is the proton NMR. And this is where I would say do the lecture note practice, do the practice active that I put up. That's all NMR, because NMR likely you'll be able to make the whole compound using just proton NMR. You don't even have to waste your time with other stuff. I would still do it. It's a good way to cross check yourself, but this is where we spend our time. This is the important bit. Okay. So I don't see anything that like sticks out as like an aldehyde or a benzene. I probably don't have a C double bond C. We've already established that. These are probably just relatively upfield because there's a bunch of oxygens. So there's nothing 7 to 8. There's no benzene. There's nothing like that. So I start with my multiples of 3. So let's say this guy, I start building fragments. This is where things really start to come together. I have a 3 hydrogen carbon. It has to have 2 neighbors because it's a triplet. Someone just asked if the exam's going to look like this. The exam has almost no multiple choice questions outside of aromatic versus non-aromatic. I put all the multiple choice questions in the quiz so I can do it's just free response. It looks just like this. All right. So now now I've got to find where those gold hydrogens are. That's almost certainly this because those are the only 2 that's only peak with 2 hydrogens I see, and I can see that there's 3 hydrogens on it. Or there's 3 neighbors, right? Because it's a quartet. So both garnet and gold here are checked off for this guy. I'm done with this fragment. It's got some R group attached to it. So I'm going to move on to this guy. Again, a carbon with 3 hydrogens on it. And it has 1 neighbor. I need another color. Let's go green. It has 1 neighbor. The green is most likely this guy. And again, he's a quartet. So he's got 3 neighbors, right? There's 1, 2, 3, 4. So he's already checked off, which means that I have 2 R groups here. So I've kind of built the 2 edges of my chain. I'm building them inwards. Then I see this peak. What does that peak look like?
Alcohol group.
It's an OH. It's almost certainly an OH. Mostly, I mean, we also know we have an OH, right? So there's got to be an OH somewhere. So that's a fragment. Okay, so I've built these fragments out and I've explained all of my proton NMR. So if you've gotten this point, I mean, you're probably talking 6 points out of 10, even though you haven't made a full molecule, right? But we're not done. I'm going to go back and look. C5H10O3. C5H10O3. So I've explained C4. There's 4 carbons I've drawn out in my fragments. I've explained 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've explained all 10 of my hydrogens. And I've explained 1 oxygen. So that means I have 1 carbon and 2 oxygens left. CO2. So this is where you have to start using deduction. I know that one of these R groups has to be in the OH. It has to be on this fragment. Because if I put the OH as this R group, well then that fragment could not connect to the other fragment. Does that make sense? There's just not space for that OH for that fragment to connect. I have to leave this end open. So I need 1 carbon. I know I've got a carbonyl. And I need another oxygen. Right? I have to fit this in somewhere. That is my 3rd fragment. Right? This is the only way I can have this fragment complete. This is called an ester. So here's the question. I can either, so if I piece these together, I'm gonna draw my fragments out. So if I can either orient it like that or like this. Then we have to justify it. Which one makes more sense with the NMR we're given? In order to figure that out, I have to start looking at shift. Specifically the shift of these 2 hydrogens and this hydrogen will tell me a lot, right? If it's this bottom structure, I would expect this left hydrogen to be really far downfield, right? It's directly connected to a carbon connected to 2 different oxygens. I'd expect that to be way more downfield than these 2 hydrogens, right? That those 2 hydrogens don't really have much pulling them downfield, right? They're 2 carbons away from 2 oxygens instead of 1. Is that what I see? Do I see that the 1 hydrogen is significantly more downfield than the 2 hydrogens? Not
No.
really. No, not really. They actually look very similarly downfield. So that seems to fit this structure more, right? Where these two hydrogens are one bond away from one oxygen, and this hydrogen is one bond away from this oxygen. I'd expect them to be very similar in their shift. And so that means that this top structure makes more sense with the shift of those two protons. So again, if you got the bottom structure instead of the top structure, you're looking at like 9 points out of 10, right? So just building the fragments gets you a few points. Doing all the different, like getting the information you can out of the graphs gets you a few points. Putting it all together makes a perfect score. So I'd probably say this is, I mean, this is a 10 out of 10. If you just wrote that, I would say if you were able to get to this point, we're going to give you a 9 out of 10. Any questions about that? No? One question. Someone said yes. Um, okay, well, I'm going to move on. I'm going to start talking about the second compound, right? Doing this, doing those practice problems, doing that active practice will help this significantly because it's really the NMR where you need to be spending your time. It's really teasing stuff out of this NMR. All right, again, I'm not going to waste my time. CH9Cl. All right, someone asked for me to explain the shift one more time. So there are two things that shift something downfield. Either it's a hydrogen connected to a carbon connecting to an electronegative thing, or it's a hydrogen directly on some kind of double bond or benzene. So if I look at this bottom picture, these blue hydrogens, the right hydrogens, they are 2 carbons away from any sort of electronegative atom. They are not 1 carbon away from an electronegative atom. They're 2. That makes a big difference. And on this, it is 1 carbon away from 2 different electronegative atoms. I'd expect the shift of this to be like 5, like be really far downfield, and the shift of this to be like 2 or 3, because it's 2 carbons away from anything electronegative. But that's not what we see. We see that they're right next to each other. They have almost the same shift. So that those shifts wouldn't make sense with these protons. These are 1 carbon away from an electronegative atom. This is 1 carbon away from an electronegative atom. So I would expect the shifts of both of those to be the same. So that's the tiebreaker. That helps me determine the top one versus the bottom one. All right. So, um, the first thing we're going to do is we're going to do the degrees of unsaturation. C, so 8 times 2 plus 2 minus 9 minus 1 all over 2. So that's 16 plus 2, 18, minus 9 minus 1. That's 18 minus 10, that's 8, that's 4. So I'm probably looking at benzene. I see a degree of unsaturation of 4. I'm thinking benzene. Moving on. There's no OH. There's no carbonyl. Neither of which is surprising because there's no oxygens in our chemical formula. There's 4 sp2s, 1 sp3. This kind of gives some credit to the benzene idea, right? And that's a lot of sp2s. Benzene would help explain why I have so many sp2s. So here, this is the one. I zoomed in to show you the aromatic peaks, to show you the benzene peaks, right? This is just this picture zoomed in. And you can see pretty clear splitting here, so that might be useful to us. We also see this. So we're thinking that there's some sort of CH3 symmetry, but there's no neighbors, right? There's no direct neighbors. Um, so I mean, if I go back and look at the chemical formula, C8H9Cl. If I have my benzene, that's already 6 carbons. I know I need 2 methyls somewhere. So they're probably going to be on this ring somewhere. So I've got to put these somewhere. So that I've already accounted for all 8 of my carbons. Then I look at the benzene peaks, right? I have 3 benzene peaks, which means that I have a tri-substituted benzene, right? So I have 3 things on benzene, somehow, some way. So the question is, how do I decide if the 3 things are like this, or if the 3 things are like this, or if the 3 things are like this? Right, those are the only 3 ways I could have a tri-substituted benzene. Well, that's when we have to look at the splitting of benzene. That tells us a lot. So it looks like I have a doublet and a triplet, a 2-hydrogen doublet and a 1-hydrogen triplet. So if I was looking at this one, I would expect 1 singlet and then 2 doublets. That's not what I have. If I was expecting this one, I would expect a bunch of singlets, right? Because none of them have neighbors, right? These are all singlets. This would be a singlet, a doublet, a doublet. That's not what I see. What I see looks more like this, where, this is going to be a doublet, this is going to be a triplet, this is going to be a doublet. So I have a trisubstitute benzene. I know that I have to have 2 CH3 groups that are symmetrical, so it makes sense to put my CH3s here. Which gives me only 1 space for my chlorine. Right, that's the only thing I'm missing here. Right. I have 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 hydrogens. So I've got carbon, hydrogen, we just need a chlorine. That's the only place I can put it. It'll save you time to kind of get more used to the benzene splitting. It'll save you time to go through, look at what a di-substituted benzene could look like. There are 3 different ways. Well, I'll talk about this on Wednesday. What does a tri-substituted benzene look like? What are the 3 different ways? How could you draw this in the different orientations? Again, if you came out and did a different benzene orientation, you would still be getting partial credit. It wouldn't be a 0, assuming you had 2 methyls off of it and a chlorine, right? You'd get credit for having a benzene. You'd get credit for having methyl groups. You'd get credit for all of these things. It's it's partly a game of getting the right answer and partly a game of when this test comes up, when you're stressed, when you're lower on time, how do you show your knowledge? Can you throw out information? Can you start just gathering data from these charts and see how far you can get? That's the game. That's true for everything in organic chemistry, even down to these reactions. Like you don't know what you're doing. That's fine. That's fine if I don't expect hundreds from anybody. I'd be shocked if there was more than 500s on this exam, but I do want to see a bunch of 70, 80, 90s of people who are starting to get it, of people who are starting to see the trends, starting to be able to say, hey, this is a nucleophile, this is an electrophile. There's going to be a bond between these two spots, almost certainly. Hey, this is a doublet. There's no neighbors. This is a methyl group. It's got two neighbors. I can start building that fragment. This is an exercise not in being perfect. This is an exercise in piecing together information and seeing patterns and trying to apply those patterns to more complicated problems. Um, all right, so here's some questions about this last question. You can just draw out CH, like you just write the line. You don't have to draw out CH3 like I did. You'll see some people will write this like this. I typically just put the two lines because I'm lazy, but some people will also write these like this, where there's methyls on the end. Um, so that also happens. But all three of these would be counted right. You know, it's it's like if someone wrote in all caps in English, you would still be able to read their essay, right? It's just a different kind of formalization. Um, yes, and also I know to put the chlorine in the middle because these two carbons have to be the same. So that leaves only one place to put the chlorine because I also knew that it had to be tri-substituted in that specific way. There has to be this symmetry through the middle to explain the two carbons having the same the protons and the two carbons having the same peak for the methyls. Because I know there's a benzene, I can look at the benzene peaks and say there are 3 total protons on this benzene. Therefore, it has to be tri-substituted. There has to be 3 things on it. Because every time you put a thing on benzene, you reduce the amount of benzene protons by that number. So I put an OH on a benzene. There's one less proton on one less benzene proton. I put a methyl on benzene. There's one less benzene proton. Does that make sense? All right. So I think that answers. Well, if you guys have any more questions about this material, the test is going to look like this. There's also a chance that I throw in, you know, to be honest, like for these mechanism ones, there's a couple things that I might do on the test that are a little bit different from this. On these mechanisms, I do kind of want you to do this last step. So I I'm going to change this to 3. Um, so I'll put out another worksheet that talks about this, but step 3 is deal with the charge. So you're gonna these first 3 steps, this is basically every mechanism you're gonna run into in undergrad chemistry. And honestly, the final step isn't that bad, right? I've got a positive charge on this nitrogen. How do I make it no longer positively charged? I take a proton. Now it's neutral. Um, this one only had 2 steps. There's no charge here, so this one's done, right? There's nothing to neutralize. This one has a charge. It's a negative charge now. So I have, this is the base that I had, right? That's this after it took a proton. So I can just take a proton. And you end up here. So I do want you guys to be able to do this. So that's my bad. I should have worded that. I will put out a practice sheet with more of these talking about this. And mostly that's because I want you guys to be able to do this step. This is dealing with the charge, right? After you attack the electrophile, there's a positive charge on this benzene ring. We need to neutralize it. And we do that by taking the proton next to it. So I do want you guys to be able to do that. But outside of that, the test is going to be very similar. There's also a chance that I give you guys like a small little like equivalent proton question if I feel like the test needs more buffer points, right? If I don't want the test to be like all hard, right? So equivalent protons or like what's the splitting, what is the integration here, to give you some free points because you guys have worked hard on proton NMR, and so I want you guys to be able to get some more points from that. So I might throw that in there, but honestly, that's something I think you guys should be able to get points with pretty easily. Yeah. Do you guys have any more questions about this test? No questions. This is all super straightforward, and you're just psyched to just show off your knowledge on Friday. You can speak. No one else is speaking. You don't have to raise your hand.
Okay. Um, are we going to need to worry about aromaticity for any of the reactions?
What do you mean?
Like, are you gonna put something that's anti-aromatic and we need to know that like it's gonna just immediately change? Like is that gonna be a key thing, is knowing the stability from that?
No, the biggest thing with aromaticity is like understanding that instead of this bromine adding into that carbocation, it reforms the benzene ring because it's more stable, right? The difference between that that reaction and if you did the same thing, if you had this with no benzene here, that bromine's almost certainly going to just add right in. But it because of these other double bonds, that benzene stabilizes it. But in terms of like, no. To be honest with you, anti-aromatic things are just very hard to make. There are some reactions that do happen spontaneously because you form an anti-aromatic thing in situ, um, which immediately reacts. But no, that's I right now EAS, NAS, nucleophilic aromatic substitution, electrophilic aromatic substitution, differentiating that from like a regular SN2, um, seeing like hydride or methyl shifts, um, knowing some like being familiar with addition reactions. Those are reactions I'm caring about on this test. And then there's gonna be a lot of arrow pushing and NMR problem solving. But no, I'm not gonna try to give you some like stacked concept of like aromaticity. It's gonna look just like this, like straight up. Like it's gonna be reformatted slightly. It's gonna be shorter, but it's gonna be basically this a different version of this practice test. I feel like this is challenging enough. I don't need to give you guys some trick questions. All right. Well, if there are no questions, then I'm gonna stop this recording and head off. But yeah, hopefully this was helpful. Hopefully this helps you guys go back through some of the old lecture notes and think about things in a different way and have a more stepwise approach to some of these problems. So yeah, I will stop this recording. And yeah, thanks for coming.